Hi, my name is Alexander Howes. I'm a senior here at San Diego State University, and my project is on speech processing. So why don't we jump right into it? Basically, this project is going to take us through the beginning, stochastic models, lexical models, and the future of what speech processing can do and its capabilities. Now, first we have to answer the question, why is it so hard? A lot of things in programming in the past have been done quickly because they're easy. But that speech processing is very difficult. The reason for this is that each person speaks at a different frequency or pitch. When I say a sound like ah, it sounds very different to you making a sound like ah, because your voice is at a different pitch than mine. Either your voice is lower or higher. It doesn't matter to the computer. All that matters is the input of a microphone is going to be different. Now, once we're past that hurdle, we're going to assume that if we could judge everyone's voice at the same frequency for the computer, then we still all pronounce words differently. There's accents. Not only that, even within what we would all consider all people with an Irish accent per se would say words differently even with that because they're stressing different parts of the word. Finally, is that even if a model could guess what the words said every single time, we still don't know what that means. So that's one of the most important parts of speech processing is knowing what the words mean and what to do with them. Moving forward, in the beginning, we used hidden Markov models. These are 1970s up to actually fairly recently, but they're colloquially known as HMMs. They're entirely statistical models that will tell you the likelihood of a single or multiple events happening. The way they work is that you have a set of known vertices and a set of unknown edges, and it just guesses until it gets it right. The best, the easiest, quickest path through the Markov model to get a good result. Basically, the way this would work is that you would input features. This features for speech processing would be about a 5-second clip of someone talking. Then it's going to divide that up into bins. These bins are going to be around 15 to 20 milliseconds. Then you take those individual bins and you make a bin of halfway in between all of them. So you end up with double the amount of features that you put in. Once you have the input and their derivative, it creates all likely outputs, and then will tell you in a stochastically constrained probability which one is the most likely. Now, there are a couple of drawbacks here. One, it's inherently discrete. It can only judge how accurate one discrete probability is to occur. So if a part of speech that doesn't really matter occurs, it's still going to get included in the information. Also, if two of them are very close, for example, if you have a 34 and a 35% measurement, it can't tell you that. It can only tell you that 35% is what was the correct answer. So several drawbacks. However, for the possibility of a single sound, if it was learning the speech patterns of one person, it would actually be perfect. But for even mild discrepancies among the input data, it's not going to be great. So we moved on from that and we got stochastic language models. Now here's where we're accounting for a little bit of the ambiguity here. Stochastically constrained models can tell you what the next word is a possibility of being. Given a syntactic model of a language, it will learn the types of sentences that are allowed and not allowed. This means you give it a library of books and it will be able to tell you that what noun, verb, adjective, adverb combinations are legal based on the inputs that you gave it. So down below, we have the fact that if you had a noun and then a verb and then an adverb, I ran fast, that's legal in the English language. However, if I said, I intelligently desk, that's not legal. Noun, adverb, noun is not something that we're allowed to do because the adverb needs to be attached to something. Now, stochastic models still have disadvantages. Data sparseness is one of them. So even in that entire library you gave it, even if you gave it 100 libraries, I guarantee that the sentence that contains that contains 7 that's, that is illegal in the English language, that's not going to be in there. So there's a lot of scenarios that are allowed that it's going to assume are not allowed because it just hasn't seen that before. Next is that words are similar. Sometimes you end up with two words that they're both adjectives and they could fit there and they sound similar, but you got the wrong one. As well as finally, you have that if you were dealing with reading libraries of books, you could have ungrammatical sentences in there. What if the editor made a mistake and you end up with an input that's faulty? It's not going to judge that next time. So these are the problems with these models, is that they're attempts to make the data fit our model. Speech is a sound, but it also has meaning. Now, when we say time flies like an arrow and fruit flies like a banana, flies obviously takes two completely separate definitions here, but in a stochastic model or in a hidden Markov model, it definitely can't tell you that. And here's where we went forward. The next step, we found a model to fit the data. The lexical language model. Lexical is the meaning of a word. What this does is it combines the rigidity of stochastic models with a flexible element, which is the judging of lexical definitions. The lexical definitions of words are able to predict the patterns based on the associated words. So, for example, if you were to give it a sentence that said the sun is right, it would input that and realize right shouldn't go with sun. Sun and right should not go together. However, I do know a word that is very similar in sound to right, that it should be, that it does associate with sun often, and that's the word bright. So here we have a lexical model handling the error of a stochastic model. This is what a lexical map looks like of a word. Here you have only the nouns, not the adjectives, that are associated with the word book. Now with book, as you can see directly above it, there's one vertex away. You have account book, book of account, ledger, and another ledger. Now, the more vertexes you are from the word book, the less likely you are to correlate. So to the left of that tree, you see a 2-vertex tree that has accumulation, aggregation, assemblage, and collection. And in our minds, when we think about it, we know that the word accumulation is less closely correlated to the word book than account book or book of accounts. This is how these work, is it's going to look for the most likely possible word instead of just what a stochastic model does, which is a possible word. The future. The future of speech processing moving forward seems to be lexical models. They're very promising. They deal with machine learning, which is very popular and up and coming code. And a lot of companies want to know that what they're doing utilizes it. It feels fast and agile. Now, these are current ASRs or automatic speech recognitions like Siri, Alexa, and Cortana all use these, and they've been viable in the marketplace. What we do know is that accents are still difficult for these models to deal with. It adds an exponential level of training data needed for the model to learn. And even if the model ends up learning it, we end up with often oversaturation. Oversaturation is when two words have the same input and should have two different outputs, or actually have one output, but should have two. Let me give you an example. If we all know the whole Michael Caine thing, there's an actor named Michael Caine from England, and if you said his name in English, it would sound normal. But if you said it in a bad British accent, it sounds like you're referencing your own drugs. This is something that when you're modeling accents might end up with two different outputs for what was wanting to be one input, whereas if you weren't accounting for the accent, it wouldn't cause this problem. So this is oversaturation is kind of a big problem right now. The solutions to this, we could make models learn to individuals. Basically, when you get your Siri, it learns your particular accent, but then it wouldn't work as well for guests you had over at your house. Another one is have predetermined accent settings. we could basically have you tell the Siri or Alexa or Cortana at the beginning what your primary language is and the reason English is, or not the reason, but obviously the fact that English is your second. And then it would deal with, use that block of data instead of the native English speaking data. And you could do that with that type of parameter. You could do that with anyone all over the world in any languages you wished. Anyways, that is about the edge of, or the end of this program. Here's my sources. Thank you so much for watching, and I will see you all in the next presentation.